Okay, we are now getting into polar graphs. All right, now we've seen a couple of short examples already. These, for example, we've already seen something like this, but we're just going to do it again real quick for review. All right, now polar graphs are not going to have x's and y's. They're going to have r's and thetas. Usually the r's and thetas are mixed together like the x's and y's are. But just like rectangular graphs, sometimes we just have graphs where they're just like x equals 3 or y equals 7. Those are kind of special graphs that are supposed to be pretty simple to graph, right? X equals any number is a vertical line, and y equals any number is a flat line, all right? So similar to that, if you just have r by itself or theta by itself, right? If it's just r equals 3, you go to the third ring, or whatever number this is. You know, if this were 5, you go to the fifth ring. If there's 1, you go to the first ring. It says 3, so go to the third ring, 1, 2, 3, and just circle it. It just means everything that's in the third ring. That's not the best kind. There you go. There's your graph for r equals 3. Done. So circles, pretend this is a nicer circle, but they're really simple and direct to do on a polar graph. That's part of the reason we have polar graphs. They're so simple and straightforward. Now, straight lines are also easy on polar graphs if the straight line goes through the origin. Now, if the straight line does not go through the origin, it can still be done, just gets a little more complicated. We're not going to get into that right now. But if the straight line goes through the origin, you just write it like this, all right? So you just have theta of 5 pi over 6. So now if you need to mark it off, remember that's your pi over 2, that's your pi, that's 0, or 2 pi, 0 and 2 pi, that's 3 pi over 2. Right, pi over 4 is exactly halfway between. Sorry, so that would actually, pi over 4 is over here, and this would be 3 pi over 4. And 5 pi over 6 would be 1 below that. So there's your 5 pi over 6 right there. So it's this line, all right, and just draw it all the way through. And boom, there's your graph. That's it. That is everything to do for this graph. That graph is done. This graph is done. A circle. And so if it's just a theta, you just draw the straight line. Okay, so pretty straightforward. All right, where it gets messier is for graphs like these. All right, this is quite a bit messier. All right, now we're going to start with example 3. All right, and now there's no quick way to do this. We have an r, we have a theta, and these are not quick. So here's what we're going to have to do. Just like back in the days when we first did rectangular graphs, we had to make a t-chart. We're going to do that again here. We're going to make a t-chart, and we're going to try different numbers for r and theta. Now, which numbers are we going to try? Well, I recommend any numbers on this unit circle. Let's start with 0, then we'll plug in pi over 6, we'll plug in pi over 4, plug over 3, and we'll just keep plugging in as we go around the unit circle. So now, remember, theta is on this side. So the angle I'm going to plug in, I'll plug in 0, I'll plug in pi over 6, I'm just getting them set up now. I'll plug in pi over 4, I'll plug in pi over 3, and then even though I'm plugging all the quadrant 1 angles. Now, technically, as we said, pi over 2 is technically not in quadrant 1, but it's kind of a neutral. It's not in either one. But I'm going to throw it in quadrant 1. So I'm going to throw in pi over 2 there as well. Okay. And I'm just going to have to actually now, just as a note to myself, I'm going to note that these are all the angles in quadrant 1. That Roman numeral means I'm in quadrant 1, because I might need to later go into quadrant 2, and I would make a separate graph for all the angles in quadrant 2. But let's just start with the angles in quadrant 1 and see what we get. Now, here's what I'm going to do. So I'm going to try to squeeze the work here. So I have r equals 4 times the sine of theta. Now, the first theta, I'm going to plug in all these different numbers in for theta. The first thing I'm going to try is 0. So the sine of 0. All right, now 4 times. Now, what is the sine of 0? Well, if you go back to the unit circle, right, sine of 0 is the y number is 0. And then what's 4 times 0? 0. So when I plug in 0, I get 0. And 0, 0 is just the origin. So even though it's kind of already a dot there, that dot is a point that's going to show up on my graph. So that's for the first point. Now let's do it again for pi over 6. R equals 4 times the sine, and this time, because I'm plugging in for this equation, right? This I'm going to plug in pi over 6. Right? I'm just making a t-chart. I'm trying different numbers for theta, plugging them in, and seeing what I get for r. Now, 4 times, now, the sine of pi over 6. What is the sine of pi over 6? The sine of pi over 6, right, if you use your little formula, is 1/2. And now I have to do, and the 4 is there. So what's 4 times 1/2? Well, that's just 2. So there I go. So now I have to graph this point, the point 2 pi over 6. So go to pi over 6, which is right here, right, and go up 2 units to the second ring. So there is that point. All right, so those are 2 points. Now, so far they make a straight line. That's good. I've only done 2 points. Let's keep doing more points because maybe this will start curving around. I'm sure it will. Most of these graphs end up curving. So let's kind of see which direction is going to curve in. So I like to plot the points as we go, okay? All right, so let's try pi over 4. All right, so r equals 4. R equals 4 times the sine of theta, and I'm going to this time try pi over 4. All right, well, the sine of pi over 4 is root 2 over 2. And when I do that, 2 goes into 4, and I get 2 root 2. All right. Now, that's a little more problematic because, like, how are you supposed to graph the point 2 root 2? So what you need to do is you need to get out your calculator and get the decimal version. And I've already actually happened to do it. And the decimal version is approximately 2.8. So I'm just going to put that in parentheses, meaning that I use my calculator. So this is the point 2.8, approximately 2.8 pi over 4. So this is pi over 4. And I go out 1, 2.8 means not quite to 3, so about there, approximately. All right, it's kind of a little hard to do 0.8. There you go. So there's 2.8. All right, so you might need to use a calculator if you get a square root answer. All right, let's go on to try this one, pi over 3. All right, so I'm doing r equals 4 times the sine of pi over 3. Remember, I'm trying to graph this equation. That's why I keep doing r time equals 4 times, because there's a 4 in the equation, right? Just like sometimes when you have a line, the slope can change. This is kind of like a slope. You can put any number you want in there, all right? So you just work it out. Now, 4 times the sine. Now, what is the sine of pi over 3? Sine of pi over 3 is just 1/2. And 4 times 1/2 is 2, all right? So I go to 2 again. Sorry, it's not 2. It's root 3 over 2. Sorry about that. So that's 2 root 3. I knew something was wrong there. 2 root 3. 2 root 3. That's like 2 root 3. All right, so you got a 2 root 3 there. Sorry, I was thinking about cosine for a second. All right, so the sine of pi over 4 is 2 root 3. Like root 3 over 2, but then root 3 over 2 times 4. The 2's cancel, and you get 2 root 3, right? 2 goes into 4 2 times. So 2 times root 3 is 2 root 3. Now again, I don't know how to graph that, so I'm gonna get a calculator. I already did it, and the calculator is approximately 3.5. It's actually 3.49 something something. So I'm just gonna round it to 3.5. So at pi over 3, which is up here, I go to like ring 1, ring 2, ring 3.5. So things kind of seem to be curving around like that, just a little bit. Right? And the last one, pi over 2, all right? So r equals 4 times the sine of pi over 2, all right? Well, pi over 2, the sine of pi over 2 is 1. So 4 times 1 is 4. So that's the point 4. These are all points, 0.00, these are all polar points, right? R and theta, 2 pi over 6, root 2 pi over 4. These are all points, polar points. So how do you find the polar point? Go to angle pi over 2, which is up here, and go to 4. 1, 2, 3, 4. All right. Now, I'm going to connect what I have so far. And here's the interesting about polar. Now, when you have straight lines, it doesn't matter what order you connect them in. But on polar graphs, you connect them in the order you've had them. So I drew this point first, this second, third, fourth, and fifth. So far, I have something like this when I connect them up. So it looks like I have half of a circle, okay? Now, I still need to do more. So this is quadrant 1. So I'm going to move this aside for a second. And now start going into quadrant 2. I'm going to do the same thing. All right, so I select R's and thetas. And now I'm going to start picking angles, because I have to keep picking until I get a full picture. All right, so quadrant 2 angles, 2 pi over 3, 3 pi over 4, 5 pi over 6, and I'll throw pi in there. All right, so 2 pi over 3, 3 pi over 4, 5 pi over 6, and pi. Now, I've actually done all the calculations already, so I'm going to save you a little bit of work. It turns, and now if you want to verify these on your own, I encourage you to do it. Turns out this is going to be 2 root 3. This is going to be 2 root 2. This is going to be 2, and that's going to be 0. And just like before, 2 root 3 is going to round to about 3.5. That's going to round to about 2.8, all right? So 2 pi over 3 is here, 2 pi over 3. So remember, this middle one is the 12s, all right? So 3.5, so I'm going back down. So 3.5 is about here, all right? 2.8 at 3 pi over 4 is about here. 2 at 5 pi over 6 is right there. And then back to 0, and it looks like when I connect them in order, and now when I connect them, I've come back to where I started. All right, so I started there. I started at 0, and I ended back at 0, right? I started at 0, and I ended back at 0. And so if I tried quadrant 3, I'm not really going to go too into it, but if I did try quadrant 3, R and theta, all right, and I started plugging things in like 7 pi over 6, it's going to turn out 7 pi over 6 is going to be 2 again. And then the next one, which is going to be 5 pi over 4, that's going to be 2 root 2. And it's just going to repeat. It's going to repeat the exact same ones. Because I already got 0, 2, 2 root 2. Right, the next one at 4 pi over 3 is going to be 2 root 3. And then the next one at 3 pi over 2 is going to turn out to be 4. These numbers are just repeating what quadrant 1 did. So what that means is I'm going around once, and then when I do quadrant 3, I come back and 4 is good. So I end up just drawing the circle twice. So it's kind of redundant. If you start noticing the exact same points, right, because the point 2 and 7 pi over 6 is exactly in the same position, right? It is exactly the same. So you're just going to get them again. All right. So it's just going to start to repeat over again. Actually, I think you can get negative. My bad. You're going to get the negative versions of these. But yeah, negative 7 pi over 6 is going to take you back. You're going to get the same points again. So things are starting to repeat. So you don't really need to do quadrant 3. Once you realize you've come back to restart it, and you're like, wait, I started with a 0. And I got a 0, even if you got them from 2 different points, you're good. As soon as the R's start to kind of repeat, you're kind of, and you notice the graph has connected. If the graph is connected, and it seems symmetric, because these graphs are always symmetric. If they seem symmetric, then you've finished your graph, okay? So if you went on to graphs 3 and 4, then, you'd just be getting the same thing again, okay? So it's just good enough to just do quadrants 1 and 2. In this particular case. And we got a circle. Now, that's the nice thing to see. I actually put in your folder this sheet, a copy of this sheet, which is all the typical shapes you could expect to get, all right? So there's our circle when it's of R equals some number, and here's a circle, and where R equals a sine, where a could be any number. And look at the graph we did, R equals 4 sine. So if I did 2 sine theta, I'd still get a circle, just maybe of a different size. Cosine gets you a circle, but it faces a different direction. You can get a graph that's called a spiral. And then, so all of these are circles and spirals in the top row. In this row here, you get these kind of sort of semi-deformed circles. Like this circle has kind of a little dimple. This circle has a bigger dimple. And then this circle has a loop inside it. These graphs are all called lemmasones. And they're equations that look like this, where A and B are numbers. Like maybe R equals 2 plus 5 sine theta. And if you did that, you'd get a graph that looks something like this. Lemmasones are kind of, again, they're sort of deformed circles. They typically have a dimple. Now, if they have a dimple, they get another name called a cardioid. Right? A cardioid is sort of a circle with a dimple. Now, it could face different directions. It could face this way, it could face upside down, but they're all circles with dimples. So circles with dimples we call a cardioid. A cardioid is a special kind of limosome. These are all considered limosomes, but a cardioid is a special kind of limosome, and they come up quite often. Right? Next, you're going to see this beautiful category here called roses, because they actually look like that, right? And they have this form here. And then down here, you have what are called lemniscates, which are figure eights, which can go across or diagonally. And again, these can all be turned around, right? So the circle, the figure eight could go that way, or the diagonals can go any direction. These can all be turned around to face any direction you want. So you have a folder like this here. These are the different types of common polar graphs. Could you imagine trying to find the rectangular version of this graph? Yeah, it's not really possible. Well, not possible, but it would be really, really difficult. But it's pretty straightforward in a polar graph, right? And these cardioids, these shapes actually show up in a lot, especially like in amusement park rides where you have spinning in multiple directions. You kind of make these sort of pathways. These are some of the pathways you make. If you know a ride called the Scrambler at Magic Mountain, if you trace the pathways you'd make, you'd get like these roses or these cardioids. That's the kind of path that you'd be making in the air. Okay, so we're going to do one more sample, and we're going to do this one right here. So we're going to take all this away, and we're going to graph this one right here. Okay, now this one's going to take a little bit of work. All right, so here we go. So we're doing example 4. All right, so again, I'm going to make a chart, a t-chart with r and theta, and I'm going to start with quadrant 1. All right, quadrant 1 always starts with 0, pi over 6, pi over 4, pi over 3, and we will throw in pi over 2, even though it's not technically in quadrant 1. Okay, all right, and we're going to work on this equation. Now, actually, if you really refer to your paper, you kind of maybe guess what's going to happen, but even so, you still don't know what size. So let's just kind of see what happens when I plug these different angles into this equation. Now, notice this is a double angle. All right, so this is how this is going to go. All right, so I'm going to plug the first one in first, 0. So I got r equals 6 times the cosine of 2 times 0. Now, just like PEMDAS, I have to do the inside first. So 2 times 0 is 0. So now I need to figure out the cosine of 0. Well, the cosine of 0 is 1. And then 6 times 1 is 6. So when I plug 0 in here, I actually get 6. All right, so when the angle is 0, this is the angle of 0. Right, when the angle is 0, I get 6. So ring 1, 2, 3, 4, 5, 6. That is the first point that's going to get me started on this graph. That's my starting point, 6, 0. Okay, now let's do the same thing for the next one. Now let's plug pi over 6 into there. So we have r equals 6 times the cosine of 2 times pi over 6. Okay, now PEMDAS, work this part out first. All right, so what is 2 times pi over 6? We'll put this over 1. 2 goes in 6 3 times. That's going to be pi over 3. So I'm really actually going to be finding the cosine of pi over 3. What's the cosine of pi over 3? Well, that's going to be 1/2. And 6 times 1/2 is 3. Right? So when I have pi over 6, which is here, I'm at the third ring. So 1, 2, 3. So there's the second point on my graph. Let's continue on. Pi over 4. All right, well, 6 times the cosine of 2 times whatever angle I'm plugging in. And the angle I'm plugging in is pi over 4. Okay, now work this part out first. So 6 stays, cosine stays. What is 2 times pi over 4? Well, 2 goes into 4 2 times. It's really the cosine of just pi over 2. And the cosine of pi over 2, last time I checked, is 0. And 6 times 0 is 0. So when I plug in pi over 4, I get 0, ring 0. I just go to the origin. All right, so that's where I'm at so far. Kind of hard to tell what this is going to be so far, even with that guidance. Okay, we're going to do next 2, pi over 3. All right, so we got r equals 6 times the cosine of 2 times pi over 3. Okay, Well, 2 times pi over 3 is just 2 pi over 3. Actually, nothing reduces this time. But 2 pi over 3 is on our unit circle. So 2 pi over 3, the cosine of 2 pi over 3 is negative 1/2. And 6 times negative 1/2 is negative 3. So when I get to pi over 3, I go actually, so I'm on, that's the line pi over 3, but because it's negative, I have to go back 3 strings. So 1, 2, 3. So I'm actually here. I'm actually here. All right, this kind of looks random, but just kind of go with me. And let's try to squeeze in the last one. All right, pi over 2 equals 6 times the cosine of 2 times pi over 2. All right, work out that. The cosine of 2 times pi over 2, the 2's cancel, it's just the cosine of pi. And the cosine of pi, it's getting a little low on there, but we'll just make it, is 1. I'm sorry, negative 1. Negative 1. All right, cosine of pi is negative 1, and 6 times negative 1 is negative 6. So when I'm at pi over 2, and this is pi over 2, I actually go, instead of going up towards pi over 2, I go back 6 rings, which is here. And so if I connect, remember, you have to connect these in order. So after I connect all the angles in quadrant 1, I have this so far. Now, I haven't come back to where I've started. This is where I started. So eventually this line is somehow going to make some kind of swiggle until it ends back there. Now, now I'm actually going to save you a lot of the work because it takes time, because it turns out we have to plug in all 4 quadrants on this particular graph, right? So when we do, this is what the chart looks like. So that's chart 1, I just wrote it again. This is quadrant 2. Now this is what you get when you plug in quadrants 3 and 4. So you have to actually plug in the entire unit circle before, notice you get back to the point 6, 0, and 6, and pi over 2. Remember, pi over 2 is the same thing as 0. So these 2 points are the same. So these points will connect up, and you have to connect all of these dots in order. Now, the reason I highlighted these 2 is because these 2 are actually a little bit trickier than they look. So I'm not going to show you how I got all of these because it's very similar to what we just did here. It's very similar, but I will show you how we did this point here, the one I marked with the star. And if I have time, I'll show you this one. Okay, so if you do r equals 6 times the cosine of 2 times 7 pi over 6. All right, so if you try to do that, something interesting, because this one works out, quadrant 2 will work out very much like how quadrant 1 did. But quadrant 3, watch what happens. You get 6 times the cosine of, and 2 times pi over 6. 2 cancels the 6, and you get 7 pi over 3. And that's the first time where, like if you do quadrant 2, everything ends up on the unit circle, but 7 pi over 3, how are you supposed to find the cosine of 7 pi over 3? Right, that is nowhere, there's no 7 pi over 3 on my unit circle. So then what you have to do is take a side mission, right? Take 7 pi over 3. What happens is you've gone around the unit circle more than once. You need to subtract from 2 pi, right? And subtracting 2 pi, you need a common denominator. So multiply that by 3, multiply this by 3, and you end up getting pi over 3. So 7 pi over 3 is the same thing as pi over 3. Those 2 are the same. It's like pi over 3 going around the circle again. So if you started here and you went all around the circle again and ended back, that would be called 7 pi over 3. So it really is the same thing, right? And the cosine of 7 pi over 3 is 1/2. And that's 3, and that's how I got that 3, all right? So that's even a little bit of extra work because then you have to convert, and you have to convert all of these, including this one and everything in quadrant 4. All these angles end up being more than 2 pi. Right? I'll do this one again. The 5 pi over 3 as an example. What happens when you plug in 5 pi over 3? I'll show you what happens there. So if you're plugging in 5 pi over 3, you get r equals 6 times the cosine of 2 times 5 pi over 3. Okay, well, that's 6 times the cosine of, and then that, nothing cancels. So you just get 2 times 5, which is 10 pi over 3. And it's like, oh, we're 10 pi over 3. I don't have a 10 pi over 3. So then kind of think 10 pi over 3 right? I probably went around the unit circle more than once. I subtract from 2 pi. I do 2 pi, 2 pi minus that. I need a common denominator, so I make that 3, I make that 6, and I end up with 4 pi over 3, and that is my unit circle. So it's really the same thing as doing 6 times the cosine of 4 pi over 3, right? The cosine of 4 pi over 3 turns out to be -1/2, and 6 times -1/2 is -3. So when I plugged in 5 pi over 3, I ended up with -3. So a similar thing happens for all of these. Now, what happens to the graph when you do all this? Well, I'm actually going to screen share, and you've seen this before, right? Desmos.com/calculator, all right? This is a rectangular grid. Here's the thing, if you click over here where it says graph settings in the top left, you'll see something like this, and look at the grid trace, that's rectangular. Look at this, click it, and you get a polar grid. So you can do all of your polar graphs, all right? So now it doesn't do pi over 6, pi over 3. It doesn't show pi over 4, but it's there, right? It doesn't label it, but it's there, pi over 2, ring 2. All right, you can zoom in a little bit if you want to see all the rings, ring 1, 2, 3, 4, 5, 6. And then you can just type into Desmos the graph you want. R equals 6 cosine of 2. And then I have to type in the theta. Now, because this graph just thinks there's no theta, it's just doing that. I need to type in the theta. Get the theta, you can go to the keyboard here at the bottom. See, here at the bottom, go to the keyboard, click ABC, and there's your theta over there. So it's kind of a few steps, but click it, and look at that. This is the final graph you end up getting. I'm going to zoom in a little bit so you can see it. That's your graph. You end up getting what's called a rose, a 4-stemmed rose, because it has 4 petals, or 4-petal rose. So that's the graph again. Now, we started with this point. When we trace the graph, we're actually going this way around the graph. All right, so it's kind of making that, and then we come back to where we started, and that would be all 4 quadrants. Now, because I know I just showed you how to do this on Schoology, how am I going to do this for the test? Well, actually on the test, what I'm going to do is I'm going to give an equation, something like that. And of course, I will give you multiple choice of some pictures and say, which picture does it look like? So to be honest, you could just use Desmos to check the picture. But what I will also do is I'm also going to ask you which points showed up on the graph. So I might say, like, does this point show up on the graph? Does this point? And I'll give you a choice of some points. Some of them would be on the graph. Some of them would not be on the graph. But that's how I'm going to be handling to make sure you've done some work on your own. So I might pick like 2 or 3 of these points and then say check, not only check which is the correct graph, but check which points would show up on the graph. And Desmos doesn't really tell you that. I mean, you can look, if you want to look really hard, if you're able to find them by looking at the graph, then it's almost as much work as just working it out. So that's why I'm going to kind of double check to make sure you're doing at least some work by hand, because I'm going to ask for what points actually show up on that picture, because it can be a little bit hard to tell just on the picture. Okay, so there's your graphing. It takes a little bit of work. Again, there's more resources available online if you need any other help. Okay.